Hi, my name is Suho Shin, and I'll present our paper, Power of Bonus in Pricing for Crowdsourcing. This is joint work with Hoyoung Choi, Yu from KAIST, and Jungsul Ok from POSTECH. So crowdsourcing is a compound word consisting of crowd and outsourcing, which represents a process of performing tasks from a crowd of people. There are many crowdsourcing platforms like knowledge sharing platforms such as Stack Exchange, completion markets like Kaggle, and Microtask platforms like Amazon Amturk, which mostly consists of simple tasks. We will focus on the Microtask crowdsourcing platforms, MCP. I will try to build a mathematical model to capture the natures in MCP. However, our model extends to further platforms on which I will elaborate later. The tasks in MCP mostly consist of simple questions. For example, classifying whether the figure depicts a dog or cat, correcting typos, or verifying spam mails. The workers in the MCP can earn money online anytime they want, and the requester can get their tasks completed in minutes efficiently. However, possibly the anonymous and transient workers might submit unreliable answers or even in spamming manner. Hence, the requester needs to smartly handle these issues. One direction is to smartly aggregate the submitted answers to infer the ground truth data. This includes several statistical inference algorithms. Another direction is to efficiently incentivize the workers to motivate only the qualified workers in advance. That is, mechanism designed for a crowdsourcing system. Our work also is included in this direction, where we focus on a specific type of mechanism which is widely adopted in the MCP. As the virtue of the MCP rises from its simple interaction, it mostly adopts a simple pricing structure called the posted price mechanism. In this mechanism, task requester posts a predetermined pricing contract for each type of workers. Then each worker arrives and strategically decides whether or not to accept the offer. And this is repeated until the budget runs out. As I briefly mentioned, posted price mechanism has several nice properties, like it doesn't have any bidding process, and the worker strategy becomes simple and clear. And obviously, they only earn from the platform. However, its simplicity leads to the emergence of spammers who abuse this platform by providing inaccurate answers, which might decrease the requester's efficiency. To overcome such a challenge, one way is to offer each worker the individually tailored contract by observing their historical behaviors. For example, one may offer a higher price to workers who provide high quality answers historically, and vice versa. And this refers to the explicit price discrimination, and there is a well-known result that personalized posted price mechanism efficiently approximates the optimal Bayesian mechanism. Another direction is to additionally reward them a quality-based bonus upon the base payment of participation. For example, one may offer the worker a participation fee of $2 and offer them additional bonus of $2 if the submitted answer was correct. This refers to the implicit price discrimination, as it maintains the pricing contract the same across the workers, but their eventual payment is differentiated by their endogenous qualities. Then optimal pricing must exploit both the personalization and bonus payment fully. However, personalization is often discouraged in practice, possibly due to some legal or privacy issues, or quality-based bonus may also be impossible due to some systematic issues as well. Thus, our main questions are, can you design a near optimal pricing without personalization? And is it even possible without bonus payment nor personalization? And finally, what is the optimal pricing structure? To briefly introduce our main results, we first define a bidimensional approximation in terms of utility and budget. And then we study price of agnosticism, which analyzes that there exists a common pricing that well approximates the optimal pricing. And We also found a power of bonus, where we proved that approximation is impossible without bonus nor personalization. And we provide some of the optimal pricing structure with respect to some canonical regimes. And we also provide an extensive real-world experiment, but we skip it in the presentation. After briefly introduce our mathematical model, I will present these results in step-by-step manner. So there are n workers, and each worker is associated with a private profile, SI and CI, which refers to quality and opportunity cost, respectively. And these profiles are private information, which means that only the probability distribution of the quality and cost is known to the requester. The requester needs to design a quality-based pricing vector P, where each PI consists of a monotone function of the worker's quality. For example, PI can be SI squared plus 10. In this case, we call the constant term 10 in the pricing function as a base payment, and the other SI squared as a bonus payment, which is actually a function of the quality. Especially if PI remains the same across the workers, then we call it the common pricing. Otherwise, we call it the personalized pricing. Note that common pricing does not need to distinguish individual workers, and hence is more feasible in many scenarios. Given the posted price mechanism, each worker arrives with private profile and accepts the offer if the payment is larger than or equal to her cost, or reject otherwise. Hence, the final allocation is decided by the identity function of the predicate comparing the payment and cost. To provide an overall mechanism description, given the budget, arrival and pricing policy, each worker arrives with respect to the arrival order, and while the budget remains, the worker is offered the pricing contract PI, and the worker decides whether or not to accept the offer, and this process repeats until the budget runs out. Eventual requester's expected utility is decided based on the allocation vector and worker qualities, and it is straightforward to check that the realized allocation vector satisfies the ex post budget feasibility, meaning that the overall payments do not exceed the given budget. Given the budget and expected utility of the requester, the optimization problem of PP is defined as the problem of finding an optimal personalized pricing. As I mentioned, our objective is to analyze the fundamental performance gap between some pricing policies. Fundamentally, to design an efficient pricing function, there exists a trade-off in balancing bonus and base payments. If we set a large bonus with low base payment, then it will efficiently motivate high-quality workers, as their payment would be higher, but it may lead to compensate top-quality workers too much, resulting in a loss of budget. On the other hand, with a large base payment but low bonus, there might be less waste of budget, as the exact amount of payments are transferred to each worker, but it cannot efficiently motivate the high-quality workers and may recruit more spammers as well. Now we get into the main results. Basically, we depict the amount of approximation in two-dimensional measure of budget and utility. Let P star B be the ultimate solution of a PP. Then we say a pricing P is delta gamma APX if it achieves delta of the optimal utility with gamma augmented budget. So delta refers to the suboptimality in utility, and gamma refers to the suboptimality in budget. Now we are ready to present our first result, price of agnosticism. Formally, it states that there exists a common pricing with 1 minus little O1 and big O1 apex ratio. It means that with constantly augmented budget, one can crowdsource almost optimally, as a little O1 vanishes in subconstant manner. The proof is based on the observations of two relaxations of OPP problem, namely ex-ante relaxation and fractional relaxation, but I'll skip the detail in this presentation. Next, I'll present our result on the power of bonus. Formally, there exists a problem instance such that no common pricing without bonus can achieve delta little ON APX for any delta between 0 and 1. It means that even with little ON augmented budget, the utility can arbitrarily be bad if we cannot personalize nor give them bonus. The proof is based on the construction of hard spammer hammer problem instance. And it basically implies that the power of bonus is crucial to achieve a good approximation ratio of OPP. So now one might wonder which one is more important among personalization and bonus. The answer is that it actually depends on the worker's profile distributions. Say that worker profile distributions are given in deterministic manner, then bonus does not have any impact, as we can exactly pay them corresponding cost as a base payment. On the other hand, suppose that we are given the homogeneous worker profiles so that all the workers share the same distribution, then it is obvious that personalization has no impact at all. So far, we study POA and POB, which measures the performance gap between optimal common and common pricing without bonus. Meanwhile, one might wonder what exactly the optimal common pricing looks like. The answer is that, again, it depends on the profile distributions of the workers. And I will now present some case studies of the optimal pricing structure in some canonical regimes. Though we focus on modeling Microtask crowdsourcing platforms, but we will extend our model beyond it and provide some implications. Since the properties of workers' profile distributions mainly are affected by the type of the task to be crowdsourced, we first present the crowdsourcing task example, and then provide some corresponding results. Let's first consider a simple and tedious microtask, such as typo correction, spam filtering, or image classification. Since the level of the task is elementary and can easily be solved, the quality of the submission would exactly be decided by the effort or time that one spends on it. As time and effort can be translated as the cost of participation, the ratio between the cost and quality would be similar across the workers. Thus, we define a ratio equivalent to regime where all the workers have the same bang per buck ratio. And then consider a linear pricing policy, which rewards the worker in proportional to her quality without any base payments. And we observe that linear pricing is optimal, which implies that one should pay what they paid. Next, let's consider a distributed crowd computing or crowd-sensing application like SETI at home. SETI at home mainly crowdsources computation resource to process a complex computation in distributed manner. And to participate in the SETI at home, the only need to do is to set a specific screensaver on one's personal computer. As the process of participation is highly simple and there is no further effort needed, the cost to participate would be almost identical across the workers. However, the quality of participation would depend on the specification of the PC and also on the time that screensaver has turned on. To describe this example in our mathematical model, the cost remains the same across the worker, but the quality varies. We define such a regime as cost equivalent regime and with parameter C0. And we consider a thresholded pricing with two parameters, alpha and beta, which pays alpha to the workers once their quality is above the threshold beta. Then one can easily check that thresholded pricing with C0 and some beta is optimal under this regime. This means that one should equally pay every qualified participant under the cost equivalent regime, and this is very intuitive since we only need to control the quality of participant as all the cost remains the same. Finally, consider a survey asking non-trivial questions. Maybe moral machine is one of the representative example. And moral machine basically asks the workers a non-trivial question on a moral dilemma and requires them to decide how they would behave in such a dilemmatic situation. In these cases, as we are interested in the opinion of the crowd, Each contribution counts as a single answer, but the depth of thinking may significantly differ for each worker. To translate this scenario into our model, we may say that the quality remains the same across the workers, but the cost can be different. We say the quality equivalent regime and find that we can always transform any common pricing into common pricing with no bonus payment without any loss of the utility, which means that bonus is not needed. This is the end of the main results. And now I'll talk about some interesting directions to explore. The first one is decision under risk. If the worker has some uncertainties in her own profile or the payment is randomized like a lottery, then the eventual payment becomes random variable and corresponding risk averse or seeking behavior may arise. Then we might need to consider such a nature in designing pricing function. And next, we have assumed that the requester can exactly estimate the worker's quality to pay them quality-based payment in ex post manner. But if this estimation process is imprecise, then it again might discourage the participation of risk-averse workers. On the other hand, if the estimation is done by collectively aggregating the participants' answers, then they might strategically collude to increase their own payoff. And then the requester might also need to consider how to truthfully elicit the answers while incentivizing them efficiently. Finally, from our observations so far, bonus payment indeed helps a lot, but it is also obvious that it increases the complexity of the mechanism in terms of both the requesters and workers. Then one natural question would be to define and measure such increased mechanism complexity and study some corresponding trade-off between the efficiency and complexity of the pricing mechanism. Thanks for listening, and here are some references I used in the presentation.